halfway through the star, talking about supernovae, novae, white dwarfs, neutron stars, and we're going to talk some about black holes today, which is exciting. So as a reminder, this is kind of the overview of stellar remnants. One stellar remnant is something that never really achieves a star at all. That's a brown dwarf. Anything that's less than about 8% of the mass of the sun just never enters the main sequence. It starts out a hot ball of gas. It stays that way. It cools off over time. You can have a sun-like star, so something up to about 8 times the mass of the sun, called a low mass star. When it dies, after entering the red giant stage, it kind of ejects its outer layers, producing a planetary nebula, beautiful nebulas, which have some other pictures of, some here. No, these are supernova ones. Showed them earlier. I think you remember these pictures of beautiful nebulae. And they leave behind in the center of white dwarf. There's a core of carbon, very dense, very hot, but that will cool off over time. Now, we talked about novae as being something that can happen. It's not a supernova, right? It's a type of white dwarf nova that can happen if that white dwarf is part of a binary star system. Remember, about 50% of stars are in a binary star system. So if you can sort of gather an accretion disk of material that swirls down onto the surface of that white dwarf, that stuff can suddenly ignite and fuse, producing a nova. We also talked about a white dwarf supernova, which is also called a type 1 supernova. If that whole white dwarf gets above, through that same process, gets above 1.4 solar masses, that's about what's called a Schwarzschild radius. So I'm anticipating something we're about to talk about, Chandrasekhar limit of 1.4 solar masses, and it'll then therefore crush down, suddenly being able to fuse all of that carbon through type 1 supernova. Then we also we're talking about neutron star or supernova. We call these type 2 supernovas for massive stars. When a massive star dies, an iron core can't support itself against the crushing force of gravity, and it can't use that iron. It pushes all that iron into a neutron star. And a neutron star is an extremely explosive supernova for the type 2 supernova. That's where we left off last time. Was talking about neutron stars. We talked about pulsars. So are a lot of neutron stars behind rapidly spinning, very magnetized objects that can sweep through space like a space light, producing flashes of light. Very that's one of them. Pulsar. Right, we talked about how they're spinning so fast they could rip themselves apart. That's one way we know that they have to be neutron stars. And X-ray burst is similar to a white dwarf nova, but when matter accumulates down on a neutron star instead of a white dwarf, it can suddenly X-ray. So that's pretty much where we left off. I figure I'll give you another opportunity to get some key, hopefully, points for participation by asking again. What is a pulsar? And more so. Okay. Yeah. And good. I think people did a little bit better than last time. It's a rapidly rotating neutron star, and it's a pulsar. Okay. one of the ways that telescopes can see neutron stars, which otherwise are very, very faint. See the pulsation. We can also see some of the more nearby ones. Other, and I also have fast line to look at also sort of points. And this one last time some people got it wrong, so hopefully my explanation last time you take to heart. How do we know that pulsars must be neutron stars? Seconds. Okay. And if people did better than last time, no massive object other than a neutron star could possibly spin so fast as we observe spin these pulsars to spin. Right? They're spinning so fast that they can only really be something like a neutron star, something that dense. I only think that could be that dense. Okay, good. So this is where we left off. Here's another question I'll go through with you, right? What causes these radio pulses? Just as a reminder, right? Why do we see pulses of radio waves? Because as the neutron star spins, so you can imagine its axis of rotation is like this, but its magnetic field axis is like this. And the radiation points along the magnetic field axis. So as it's spinning, this magnetic field axis and the sweep, like a searchlight of radiation, is sweeping through space like this. And if one of those beams happens to cross through the Earth, then we see that pulse regularly every rotation. Any questions about pulsars? Now, so we talked about white dwarfs and how most stars, well, about 50% of stars at least, have a companion star. And when you have a companion star, one of them dies first, it becomes a white dwarf or neutron star. It can gain an accretion disk from that nearby star. So there's an illustration of a nearby star, and a lot of that material is falling down into a neutron star. If we talk about white dwarfs, this produces a nova, type of nova. When this happens around a neutron star, the exact same thing can happen, but it's called an X-ray burst. In fact, we also see that the neutrons that we can actually watch, if it's a pulsar, we can watch it spin increase as that material swirling down adds angular momentum to the neutron star. And then we can also see, like just as we do with white dwarfs, repeated episodes. More stuff swirls down, it suddenly fuses, produces a burst. Okay, and instead of so for a neutron star, it's so much denser, gravity is so much stronger, pressure is so much higher that these bursts happen faster and more powerfully, but briefer time. And so we call them an X-ray burst because the light produced is higher energy X-rays. So it's pretty much the same thing that happens on white dwarfs. They produce nova that on a neutron star produces what we call an X-ray burst. And you see just how short they are. So we suddenly see a burst of X-rays, 10 or 100 times stronger than normal, that only lasts a second or two. So all that energy is very quickly. That's called an X-ray burst. Now, I want to talk a little bit about black holes. And that lets us talk a little bit about relativity, which is a really fun topic. I'll do my best to describe to you this. It's kind of a topic that you learn later on in physics, but that I can, I think, explain pretty well to you at the level of this course, and it's kind of fun. One thing we mentioned before, let me try to go back to that slide, is that if you could imagine looking at a neutron star, already this isn't a black hole, but a neutron star is so compact, its gravity is so strong that it's actually bending light. And we'll talk about this more, but I just want to go back to this to remind you just how kind of weird things get when you get to really strong gravity. Light is being bent to the extent that if you put a checkerboard pattern over this neutron star, since this was the North Pole, this was the South Pole, you could see behind it, right? This area, if you looked at the neutron star, you would see behind the neutron star because light from behind the neutron star is getting bent by gravity around towards your eyes. So you're seeing most of the back of the neutron star in this picture because gravity is so strong. Okay, these are the sort of effects we start to talk about when we talk about general relativity. And one thing we'll talk about now is the bending of light through the relativity. So it's one thing to understand about relativity. So there's two theories of relativity, both of which were invented by Einstein. Einstein, by the way, he's kind of a household name, right? And it's for good reason. He really did discover a lot of stuff, and you might be familiar just with relativity, but first of all, there's two theories of relativity, both of which are groundbreaking. One's called the special theory of relativity, the other is called the general theory of relativity. He also made really important contributions to quantum mechanics that he won the Nobel Prize for. He made important contributions towards the discovery of evidence for the atom, the atomic theory of matter. Anyways, he was a really important figure. So it makes sense why he probably knows them. But so relativity has two theories. The first was in 1905. Okay, this we call the special theory of relativity, and it doesn't have to do with gravitation, but it is important. There's two postulates of relativity. One is that the laws of physics are all the same in all inertial reference frames. What do we mean? We mean that if you're on a train or an airplane and you do an experiment, you throw a ball up, lands back down in your lap. Any experiment you do is this going to give you the same result, whether or not you're in a moving train or a moving airplane. And by inertial, we mean that train or airplane is moving in a straight line, it's not accelerating. So of course you'll feel weird if the plane is veering off, but if it's just going straight, no matter how fast you're going relative to the Earth, you can't tell whether you're moving. All your experiments are the same. That was one postulate of relativity. The other is that the speed of light is the same in all of those reference frames. So if I'm in an airplane and I look at the light from the sun out my window, I'll measure the same speed of that light as someone on the Earth. And that's actually really weird because you're moving different on the Earth relative to the train, but you both measure the same speed for when you look at the sun. So that's what gives rise to these weird effects in relativity that have to do with when we talk. You've probably heard, and we mentioned some in this course about things like time dilation. Time is different for different observers. People's clocks run differently between the train and the Earth. Distances start to get squished and weird, and all that happens in such a way that both of those observers measure the same speed of light. That's the special theory of relativity. Now, 10 years later, Einstein came up with, in some ways, a even more revolutionary theory called the general theory of relativity. What he noted was something that you might take for granted, which is that we often just say mass when we talk about F equals ma. We say mass, and in the gravity formula here, we just plug in mass. But these two things are actually different. So in F equals ma, what does mass mean? It means how hard is it to accelerate an object. That's what the mass means in F equals ma. That's what we normally mean by mass. But if you plug mass in this gravitational formula that tells you how strong gravity is for something, that's totally different. That has nothing to do with how hard it is to accelerate an object. That's how strongly it gravitates. And so what Einstein noticed was called this equivalence principle, which is that it seems strangely that inertial mass, which should have nothing to do with the other mass, we might call the gravitational mass, are the same. And the result of that is profound. It means that if gravitational mass, that's how strong something pulls on it, is proportional to its mass, to gravity, and inertial mass, that is how hard it is to push something, if those are the same, then there's no distinction between what you would consider an accelerated frame, meaning if I'm in an elevator and it's accelerating upward, I'm pulled downward. There's no distinction between that and being pulled down by gravity. Okay? In other words, there's some deep connection between gravity and just being in a frame of reference where, like being in an elevator or a roller coaster, where you feel these forces, but they're not real forces. You just feel them because they're being pushed around. This was the deep Einstein principle that Einstein based his general theory of relativity on. And we can kind of understand it by picturing people in elevators. I think this is a good way of understanding Einstein's theory of relativity. Okay, so imagine two people are in a box. It's kind of like an elevator. Two people are in a box. There's no windows. Can't see outside. There's one person on Earth in a box, and they watch an apple fall down. Okay, they do some experiment. They hold an apple, they drop it, the apple falls down, and you say, hey, that's gravity. Well, what if you put the same person in a box? It's a spaceship out in space, and it's accelerating upward, okay, where the rocket's thrusters are moving. Now, the person in space is going to do an experiment where they hold out a rock or an apple, and it'll also fall down exactly the same. Now, the reason why is because as the rocket pushes out its exhaust, the bottom of the rocket is being pushed up. So as the person drops the apple, the bottom of this box moves up to meet it. And as a result, if you're in the box, you drop an apple, it's like there's gravity, and everything feels exactly like there's gravity. It feels exactly like you're on Earth. There's no difference between standing on Earth or being in a rocket that's accelerating upward. This is the principle of equivalence that Einstein used to kind of derive all of these consequences of general relativity. And we're going to see an example in a second. The converse is also true. Now, suppose you have someone on the left, you've taken away the Earth. Or alternatively, you put them in a box, but you've taken away the ground. You know, the box is just falling. We call it free fall. So you put someone in a box, it's like an elevator where you snap the cable. The box is just falling. Well, what's going to happen for this person if they try to drop the apple? So if this person is standing in this box, it's just falling, and they try to drop the apple's going to float there. It's going to be like they're weightless. Why? Because the box is falling, the person is falling, the apple is falling. Everything's falling at exactly the same rate. So if you try to drop an apple, well, it's falling. But so are you. So is the floor. Everything's falling at the same rate. So everything feels weightless. Exactly the same as if you were in outer space in the middle of, a light year from the nearest star. The experiments will be exactly the same. Okay. So free fall in a gravitational field is exactly the same as not being in a gravitational field at all. And so these sort of ideas are allowed Einstein to derive all sorts of consequences. So let's derive right now the fact that light bends in a gravitational field. Okay, so let's imagine then that you're on a spaceship. Okay, because we're going to use this fact that being on a spaceship is equivalent to standing on Earth. So imagine, first of all, imagine you're in a spaceship that's not accelerating, and you shine a flashlight through the left window, through the right. So this is an example where the spaceship is still relative to this. Right? What happens if the spaceship is moving up at some velocity? If it's not accelerating, it's just moving up. Well, what happens is the light enters through the left window, and then before the light gets to the right window, the spaceship has moved up a little. So the light looks kind of slanted from the perspective of the person in the spaceship. Now, imagine that the spaceship's firing its thrusters and it's accelerating upward. Well, what happens? So the light enters the left window just as before. But now, as the light is moving this way, the rocket is moving up, and it's moving up faster and faster. It's accelerating. And as a result, the light is going to appear to fall down towards the floor of the spaceship. In other words, it looks from the point of view of the person in the spaceship like the light is kind of gravitationally being bent downward. That's just normal physics. That's not invoking relativity. The general relativity says that this is equivalent to standing on Earth. Because, like we said, standing on Earth in gravity is the same as being in a spaceship that's accelerating upward. And so this is Einstein's derivation of the fact that light bends in a gravitational field. So if you shine a flashlight on Earth, it bends downward towards the ground. Now, you don't notice this because it bends a very small amount. It bends more and more strongly near more massive things like the sun, or even more massive things or denser things with stronger gravitational fields like neutron stars or like black holes. That's the most extreme example. Black holes bend light so much that the light, if you tried to shine upward, it'll just bend right back down. So that's why we call them black holes, because you can't see the light from them, because light just bends right back in them. So this was one of the first major predictions of general relativity. Let me give a list of various predictions and consequences of general relativity in physics. So, first of all, what Einstein explained was that all of this can be understood as being the result of space-time itself being curved. That is, something with mass, like the Earth, literally bends space and time, what we call space-time. And the rule, he said, as a consequence of all of this, is that, oh, what paths do things? If I throw an apple up in the air, what path does it follow through space-time? It follows a straight line through space-time. The way to understand that is sort of like if I draw a straight line on this piece of paper. So I've drawn a straight line. So this really is a straight line. But if I curve space, or if I take space and curve it, what is a straight line begins to look curved. That is the nature of why things with mass that cause kind of indentations in space-time like this cause, a comet to whip around and get curved around the sun, right? Gravity is a consequence. Gravity, what looks like gravity, gravitational attraction, is just stuff curving through space-time due to trying to follow a straight line through a curved space. And as we'll see when I get to the bottom of this list, we now have clear evidence for curved space-time. Another piece of prediction is what's called gravitational lensing. If light can be bent by gravity, then things with larger mass and more gravity will bend light more. And I'll show you some pictures in a second. You can see light being lensed just as though you put a giant lens in outer space by things that have mass, because things that have mass cause light to bend. So one of the other big early pieces of evidence was that exactly for the same reason I actually described. Here, let me draw another picture. So we learned Kepler's laws that planets follow ellipses. Imagine this is Mercury orbiting the sun in an ellipse. Now the Mercury is the closest to the sun, so it's the closest to the sun's strong gravitational field. And because of Einstein's theory that space is curved, if I make a tear in this paper so I kind of curve this paper a little bit, now you see that the orbit of Mercury no longer matches up. That is true. Let me extend this straight line then. If I extended the straight line a bit, you see that the orbit no longer matches up into a perfect oval. It kind of starts to follow a trajectory that wanders around. That's called precession. And that was measured and seemed to confirm Einstein's theory. That's a consequence of just space being curve, and that precession is largest for Mercury because it's closest to the sun. It's most affected by that curved spacetime. I'm going to show you some pictures in a second of how we can visualize curved spacetime. Another thing we'll talk about is gravitational redshift. The fact that if I shine a flashlight up, it loses energy in the Earth's gravitational field. Light always goes the same speed. So how can it lose energy? It gets redshift. Its wavelength increases. It gets redder and redder as light exits a planet. You shine a flashlight downward, it wants to speed up, but it can't speed up. It's always the same speed. It gets blue shift. Another consequences of relativity is if light can't escape something with enough gravity, because light is so bent that it curves right back into it. We call it a black hole. No light can escape some objects that have so much gravity that we call them a black hole. We'll talk about gravity waves. We've literally observed now space-time itself waving, ripples in space-time. And this is like direct evidence of the fact that space-time can be curved. If space-time can be curved, it can ripple. And we've measured that ripple. Finally, another consequence that will be relevant to a later lecture when we talk about cosmology is the universe as a whole. The universe as a whole can be curved, that can have consequences. The universe as a whole can expand and contract. These are consequences of general relativity. So I'm going to go through some of these. One thing, this idea of the space-time to be curved, it's kind of interesting to go back and talk about. When you learn in grade school two-dimensional, what we call Euclidean geometry, that is where you're drawing triangles. Triangles have 180 degrees. You have straight lines, parallel lines. That's called Euclidean geometry. That relies on 5 postulates. The postulates are that it's possible to draw a straight line from any point to any point. Sounds reasonable. It's possible to extend a straight line continuously in a straight line. Seems pretty reasonable. It's possible to describe a circle with any center and radius. Seems reasonable. All right angles are equal to one another. Seems reasonable. But then there's this 5th postulate. Given a plane and the line L and a point, there is one and only line parallel to that other line that passes through that point. This is the 5th postulate that is not true in curved space. So these are called non-Euclidean or alternative geometries. And this is a Euclidean geometry is one where, as I just described, you have a line like this blue line and a point. There's exactly one line shown in red that's parallel to that blue line that goes through that point. That's the usual Euclidean geometry. But if space can be curved, then you have 2 possibilities other than that. One is called an elliptic geometry, and it's shown here. If you try to draw two lines, there's no line that's going to be parallel to this blue line. They always intersect. That's what we mean by parallel, whether or not they intersect. Okay, so if I try to draw a line through this point P, there's no line that I can draw that won't eventually intersect this. I'll show another example of this, like the surface of a sphere is like this. You can't draw 2 lines on a surface of a sphere that won't intersect. An elliptic geometry. The other opposite possibility is called a hyperbolic geometry. And there you can often draw multiple lines that won't intersect. Multiple lines, like as shown here, that are always curving away from each other. Okay. So these are 2 possibilities. One is called alternatively called positively curved. So it's like if you're living on the surface of a sphere, first of all, you can't ever draw 2 lines that won't intersect. If I try to draw nice, so look at these lines of longitude. If I follow this line of longitude and this line of longitude, you might think they're parallel, but hey, they intersect at the north and south poles. Can't draw 2 parallel lines. They also have other properties. Like if you try to draw a triangle on the surface of a sphere, the angles don't add up to 180 degrees. They actually add up to more than 180 degrees. You can see this in an extreme case. If I draw a triangle from the North Pole down one of these lines of longitude, down around the equator, and back up to the North Pole, these 2 angles here have 90 degrees each. I can make it so all three angles have 90 degrees, which is really extreme because that means that the triangle has 90 degrees more than it normally should. The opposite possibility is called negative curvature. And here's an example, like the surface of a saddle is an example that has kind of the opposite property, where if you draw two lines, they keep diverging from each other. And if you draw a triangle, it's the opposite. If you draw a triangle, that's less than 180 degrees. There's the two possibilities. If you live in a curved space-time, like we think we do, you try to draw a triangle or for example, the angles won't necessarily even add up to 180 degrees, even though that's what you learn in geometry. Now, to anticipate something we'll talk about later in cosmology, to the best of our measurement, space is very close to flat. So don't worry about this. If you draw a triangle, it would have to be miles large before we'd ever have to possibly worry about the angles not adding up to 180. But this is the reality of living in a curved space-time, these sort of possibilities. Now, what Einstein's general relativity says, when I kind of jump to kind of the more rigorous formulation of it, it says that the curvature of space-time is proportional to the energy density. Now, what's a source of energy density? Mass. So we're mostly talking about mass. So here's an example of like space-time. Imagine this kind of grid here. And I put a little small mass here. It indents space. If I add mass, it indents space-time more. If I add bigger mass, it indents space-time more. And as a result, you get orbits of planets and things that are more and more tightly constrained. They want to orbit closer and closer to that mass because of that warping of space. Gravity, this idea of gravity, is a manifestation of curvature. It's very similar to if you put two bowling balls on a mattress, what am I thinking of? A place to jump. Right? They will tend to roll towards each other. Okay? It's because they each bend space-time in a way such that they each want to try to then follow a line that connects the two. So this is what happens when you make curved space-time. You put masses in it, they attract toward each other. Another example of a prediction of general relativity is this, and this we went through, we kind of derived this ourselves, that light is bent by gravity. So one way that astronomers tried to think, how could we measure light being bent? Well, what's the most massive thing we know? It's the sun. The sun is the most massive thing we know. And if we want light to be bent by the sun, we want to look at light rays that go as closest to the sun as possible to see if they get bent. So the idea was, okay, let's wait for a solar eclipse and look at stars so that the starlight is coming just right across the surface of the sun and see if it bends that light so that the star moves in the sky. This was confirmed by Arthur Eddington in 1919 by watching saw that stars were deflected by 1.75 arc seconds. Oh, no, he saw that it was 1.61 arc seconds. Predicted to be 1.75 arc seconds. So this was the first confirmation. That's pretty good. That's the first confirmation of gravitational starlight as predicted by general relativity. And nowadays, we see lots of evidence of this. So this is what we mean. So here is a star, say, emitting light, and here's where the light goes, right? So the light is coming this way, and it gets bent this way by the sun. So say, normally you're standing here and you see the sunlight from that direction, but as the sun moves and it starts to intersect with the pathway of this light, suddenly it gets close enough that it bends the light, and now it looks like the star's over here, right? You see the light coming this way, so it looks like the star moved from here to here. That's an example of what we're talking about in this case. And nowadays we see all sorts of telescope images, especially from Hubble, where we see all these smears of galaxies. This is an extreme case, but something we see all the time, of gravitational lensing. Okay, what we see here is all the bright stuff is like this is a cluster of galaxies. Now, a cluster of galaxies has a tremendous amount of gravity. Because we're not just looking at one galaxy, we're looking at hundreds of galaxies in a cluster. And what happens is they have so much gravity that you can see a galaxy behind those galaxies whose light gets deflected and smeared around, even into like circles. So here you're seeing a galaxy, just one galaxy that has like duplicate images, and it's smeared out here. Here you kind of see it smeared all around. And it's being lensed exactly as though we're going through like a glass lens. And that's called gravitational lens. There's another case, this is called the Einstein cross, where you see a quasar. This is basically a bright galaxy that we see imaged 4 times. There's 4 copies of it, because there's a galaxy in the foreground whose gravity has bent the light from that background quasar into 4 copies, and also magnified it to make it brighter than it otherwise would. So it really does act like a lens. You can use gravitational lensing to kind of magnify and see even more distant galaxies behind more galaxies that are closer to us. Any questions about gravitational lensing? It's just it's one of the most used things in astronomy. That's very cool. So another thing I mentioned was the perihelion, the precession of the perihelion of Mercury. What do I mean by that? Well, Mercury, as I showed before with this piece of paper here, according to Kepler, should just follow this ellipse. It should just stay in this ellipse forever. But because, so it would be following an ellipse like this forever, but if you curve space-time, suddenly the ellipse, the starting and ending point of the ellipse don't meet up. And so what happens is each time Mercury goes around, it draws an ellipse that's shifted, it's precessed slightly. So it keeps moving around. It precesses by 43 arc seconds per century, so it's not a lot. This image here is exaggerated. But this is predicted, and it's correctly predicted by general relativity. So the precession of the perihelion specifically means the closest approach keeps shifting by 43 arc seconds per century. Another piece of evidence or piece of prediction and evidence of general relativity is called gravitational redshift. So if you imagine throwing a ball up in the air, it loses energy, right? It slows down. Well, if you point a flashlight up in the air, it also wants to lose energy. It does lose energy, the light. But the light can't slow down like an apple. So instead, the light just stretches. That's called gravitational redshift, as predicted by Einstein's relativity. So if you're looking at a star, all the light from the star is actually redshifted a little. It's a little bit redder than it would be. Now, that's not a big effect for a star like our sun, because our sun isn't massive enough. But if you start talking about things like neutron stars, or even more extreme black holes, a neutron star's light is really redshifted. So the light we see from a neutron star is a lot longer wavelength than it really was when it was emitted due to this effect. Black holes are even more extreme, such that you might say, right? So a black hole we talked about, it's a case where if you shoot like a laser out of a black hole, it'll like bend back down, right? It won't ever be able to escape, right? That's what we call a black hole. And you might say, well, what if I shoot it straight up so that it can't bend left or right? What happens? Well, gravitational redshift just gets redder and redder and redder until you can't see it at all. So if you were to watch your friend fall into a black hole, they would get redder and redder and redder until you couldn't see them. This was, by the way, confirmed experimentally. You can like literally just put, shine light up and down a tower and measure this with atomic clocks. Yeah, so just kind of to confirm that you're following along, right? Which of the following correctly describes how light will be affected as it tries to escape a massive object? Well, think of how anything trying to escape a massive object, gravity is pulling inward, it's losing energy, it's struggling to get out. So light, in the case of light, it can't slow down, but it can lose energy. What has lower energy? Redder light. Longer wavelengths of light have lower energy. So we say it's redshift, and the light gets redder. And not literally redder, sometimes it can be shifted from X-rays to the blue, or from blue to yellow, yellow to red, red to infrared. What we mean by redshift is the wavelength gets stretched out, but longer and longer wavelengths. Okay, and so if space can be curved, it can also vibrate. It's like, think of it like the surface of a mattress, right? Curve the surface of a mattress, but if that can happen, well, you can wiggle the mattress. The whole thing can wiggle. And when pretty major events happen in space, such as neutron stars orbiting each other or colliding, black holes orbiting each other or colliding, they produce ripples that we can measure on Earth. Now, the first measurement of this was indirect. We watched neutron stars orbiting each other. So in 1993, a Nobel Prize was awarded because someone in the 70s had watched this. They watched neutron stars orbiting each other and saw that they were losing energy. Like the orbital velocity was changing because that energy was leaving. How? Well, it was predicted that the way they were losing energy was through gravitational waves, as predicted by Einstein's relativity. This wasn't directly confirmed until 2015. Well, the 2015 Nobel Prize from what was for measurements from LIGO from a few years before, proving the existence of gravitational waves from these merging black holes and neutron stars. And I'll say some more about that in a second. It's really interesting. This is so here's an illustration of what we mean. You have two black holes or two neutron stars, two things that are really have really strong gravity. If they're orbiting close to each other, that really strong curvature of space-time is kind of being emitted out as ripples. Let me go to the picture of LIGO for a second. The way the detection here of these waves work is you have two really long arms with lasers in. So you see that here, like this is LIGO stands for Laser Interferometer Gravitational Wave Observatory. So these two like multiple kilometer long arms with lasers in them. And when a gravitational wave moves through this detector, it's literally causing space and time to contract and lengthen. So when a wave passes through this, one of the arms will get shorter while the other arm gets longer. And you can measure this as a vibration in your signal through what's called an interferometer. Okay, so this is really remarkable. And what LIGO has been doing is, because what can be seen are these rare cataclysmic events when neutron stars or black holes spiral into each other, producing gravitational waves. LIGO has started measuring neutron stars and black holes merging into larger black holes. So this was one of their first publication plots that I wanted to show first because it's starting to get crowded, because it's kind of amazing what they've done. But basically, in yellow here are like known neutron stars, right? So we can measure neutron stars, we can look at pulsars. We see that they have the predicted mass range between 1 and 2 solar masses. But then there's kind of a region where we stop seeing them because that's above, remember, the limit, the TOV limit, the Tolman-Oppenheimer-Volkoff limit, beyond which they would collapse into a black hole. So we stop seeing them. And then there's a region, and I'll talk about this, where we can infer black holes, this is in purple, in binary systems. You see binary systems where, remember, through Kepler, we can infer their mass. And we figure out they have such high mass that they must be a black hole. But what LIGO measured could measure the actual black holes and then measure the actual energy that they formed when they collided. So shown in blue are the examples of measurements in like 2015. They've now measured a whole lot. So this is what the sort of thing they're measuring all the time now. Like 20 solar mass black holes, combining with 40 solar mass black holes. 30, 40 solar mass black holes combining to be like 60 or 70 solar mass black holes. It's really kind of amazing. So we're really starting to explore and understand the range of black hole masses by seeing these rare kind of cataclysmic collisions between them when they spiral into each other. And we're learning a lot. So like we see, for example, as expected, we expect to see like 5 solar mass black hole combined with the 6 solar mass. These are expected masses, right? We expect black holes to have masses somewhere above the TOV limit, so somewhere above 3 or so solar masses. We see these lower mass black holes combining to form larger solar mass black holes. What's interesting is there's a range called intermediate black holes that are too large to have been formed from stars. Remember, like an individual star can't have more than 150 solar masses. So there's no way you can combine stars to get a black hole above a certain range. So actually, LIGO recently discovered the first intermediate black hole, and the only way you can produce that is through the merger of 2 black holes formed from stars. So a black hole of intermediate mass range couldn't have been formed from stars. It had to have been formed by colliding with another black hole. And so that's something we're measuring. So LIGO and Virgo are interesting. So in order to measure these gravitational waves, you have to be incredibly sensitive, right? You are measuring vibrations from something that happened a billion light years away, causing space-time to wobble. And they're so sensitive, they will measure like a truck driving by. They have to be so sensitive that because just a truck driving by set off the detector, they have other detectors around the globe. So for example, Virgo is one in Italy that try to detect at the same time. And if they both make a detection at the same time, it's unlikely it was because the truck was driving by, right? So, and then hopefully soon we'll send one of these detectors into outer space where we don't have to worry about that. And that'll kind of revolutionize this aspect of astronomy. Okay. I went out to visit here a few years ago, actually. It's really neat. Anyways, good. They can measure, in order to be sensitive enough to measure gravitational waves, they literally have to be sensitive enough to measure vibrations much, much smaller than the width of the proton. And so it's absolutely remarkable. All right, any questions so far? Cat enjoying the sun. Can you see that? Hi, Parsley. All right, so black holes. Let's talk about black holes. Here's a simulated image. Now, one thing about black holes is that you can't see them directly. I mean, there's a couple of reasons for that. One is that they're black holes. They don't emit light, right? Light. The whole point of a black hole is that something whose gravity is so strong, light can't escape it. So you can't, at best you would just see a black hole, which is in the name, right? You'd expect you'd be seeing stars, and then suddenly a region where it's just black. But the other problem is that, like any object in space with a lot of gravity, it attracts stuff around it. It has an accretion disk. So in reality, there's going to be all sorts of dust and gas swirling around this thing, making it hard to actually see the black hole. So we've never actually seen directly a black hole. Also, the size of the black hole is small enough that it'd be hard to resolve it. But this is a simulation of what you'd expect to see if you could, okay? Because the main issue is that there's a region where light can't escape, but anywhere near that, gravity is so strong that it's bending light around. It can cause light to wrap around many times before coming towards your eye, and it causes very cool distortions. So here's an example where you might not have noticed in that last image, but you have multiple copies of the same thing. So here encircled in blue, this is a galaxy. You see a copy on the left, you see a copy on the right. That's because some of the light from this has gone the opposite direction, but then been curved around by the black hole back towards our eyes. let's see, here's another example. This here is, you see a copy here in yellow. Okay, these two are copied here with the pink circle. In any case, the point is that it's getting so warped that it's almost hard to comprehend what's going on. You're seeing light, like it's like there's a mirror reflecting, this thing on the left. Light gets wrapped around towards your eyes on the right. You're seeing a copy of this whole kind of cloud of gas and dust up here. This region here is being copied down here. You see another copy here and here as you have multiple wrappings of light around the black hole. Anyways, it's a very extreme situation where the warping of light is pretty extreme. Here's a general summary of some of the black holes. A summary of some of the properties of the black hole. First of all, what is a black hole? It's a region of space-time where gravity is so strong that light can't escape. So not only can you not, you can't be an astronaut taking a spacecraft down to a black hole and escaping. You definitely can't escape. But even light can't escape. Couple of properties. One, black holes are really, really simple. This is called the no-hair theory. They're the simplest objects in the universe. Once something falls into the black hole, it's just black. You don't see anything except the mass of the black hole, how fast it's spinning, and its overall electric charge. If you drop charges into the black hole gets charged. They also have a size. Okay, they can range in mass from just a few solar masses, in which case they're a few miles in size. Smaller. Remember, a neutron star is like the size of a city. Black holes are going to be even smaller for the same mass. So you can be just a few miles if you're a few solar mass black hole, all the way up to, we'll talk about a case like a supermassive black hole at the center of our galaxy, in which case the black hole would be like the size of our solar system. Now, how do you form these? Well, a star with a mass above like 20 solar masses produces a core that's larger than that TOV limit, right? That iron core that would collapse to a neutron star is so massive that it will just keep on collapsing to a black hole. We also mentioned the case that if you do form a black hole, you can form other black holes through collision. So when we talk about a black hole, there's kind of two regions that are important. One is the idea that, well, first of all, if things are falling into a black hole, they're just going to keep falling down into the very center, into what we call the singularity. Okay? This is a place where if we imagine space-time curving, it starts to curve down to infinity. So in math, we use the term singularity to refer to something that goes down to infinity. It starts to become kind of mathematically ill-defined. No one knows for sure if this actually happens, the singularity. It might be that some new physics comes into play that prevents it from stretching infinitely down. But regardless, far away from the singularity, you have what kind of defines the observable property of a black hole, which is the event horizon. That's the location in which no light can escape it. Right, so the singularity might be way down here, but the event horizon might be, say, what's shown in blue here. You get that close, you can't escape, light can't escape, and that's what's like the black region of a black hole. That event horizon has a formula. It's about 3 kilometers times the fraction of our sun's mass. So if your black hole is about the mass of the sun, then the horizon is going to have a radius of 3 kilometers. If you're 100 times the mass of the sun, then the event horizon is going to be 300 kilometers. Now, if you're going to fall towards a black hole, there's a couple things to know. One is that because of Einstein's theory of general relativity, falling towards a black hole, if you're in free fall, should be the same as being weightless in space. You shouldn't feel anything. And that's basically true in that you can pass the event horizon without ever feeling anything. For really, really large black holes, in fact, you would just pass the event horizon without noticing anything was weird at all. Ultimately, you could never escape the black hole. If you're inside the event horizon, but nothing weird would have happened. For smaller black holes, something else does become important, which is called spaghettification, which is kind of what happens to your body if you get too close to something that is pulling more on your feet than on your head. Those are the tidal force. Now this happens on Earth, right? On Earth, the moon is pulling more on our heads than on our feet, right? And this is why the ocean tides happen. But it's a very small force on Earth, right? We don't have to worry about that from the moon. But if you get to something like a black hole whose gravity is changing a lot from place to place near it, you can't have a case where if you're dropping towards a black hole, your feet get pulled into a black hole before your head has, and it'll stretch you out. That's called spaghettification. Now, kind of one of the simplest kind of black holes you can model is called the Kerr black hole. It's one that's just rotating. In which case, just like anything that rotates, its arms want to pull outward. So in this case, you have an event horizon that's shown in black. But you also have an interesting region called the ergosphere, where if you get into that region, you're kind of pulled along with the black hole. You know, it's like a swirling whirlpool, and you can't kind of move in an opposite direction here. You're pulled along no matter what, that ergosphere rotating around the black hole, no matter how much you try to struggle against. Now, the idea that black holes are really black is actually not true. I mean, it's true in practice, but there is something, a result from Stephen Hawking. This is one of the reasons why Hawking is famous, called Hawking radiation. Hawking proved that black holes actually do emit light. As such, they can evaporate away. If you have a black hole, it will eventually radiate if stuff's not falling into it, but it'll eventually emit energy and eventually dwindle to nothing. It takes a very long time. Okay, it takes 10 to the 67 times the ratio of your star to the sun's mass cube in years. So in other words, if you're the same mass as the sun, it's going to take longer than the age of the universe. If you have a black hole that's 100 billion kilograms, which is actually pretty small, 100 billion kilograms, then it would evaporate in 3 billion years. The point is that black holes actually do emit a tiny amount of light, but it's so little, for all intents and purposes, it would look dark, look like a black hole, and it's not really relevant unless the black hole happens to become really, really small. But when it does become really, really small, it decays kind of like any unstable elementary particle. It starts to just behave just like a little particle. It evaporates, it decays. So it was kind of a beautiful relationship with particle physics. I'm going to talk about some of these details. So yeah, so I mentioned the masses of black holes. You can have a stellar mass black holes. These are what form from stars. They're everywhere, anywhere from about 3 solar masses up to about 15 solar masses. And this just happens if you have a really large star. Remember, if it's more than about 20 solar masses, when it undergoes supernova, that iron core is so massive, when it crushes down, it'll be above that TOV limit. In other words, above the limit beyond which that neutron star can't stay stable. It'll all just crush down to a black hole. There's a famous example. I'll show a picture of Cygnus X1. Then there's intermediate black holes. These are, you might see these in the cores of, for example, large star clusters, maybe low mass galaxies. And LIGO has seen them produced from the merger of stars. The point is that you only get intermediate black holes if stars start merging, or black holes start merging together. And you have extreme cases like that called supermassive black holes that you tend to find in the center of large galaxies. So these might be black holes more than 1 million solar masses. In other words, you have some black hole in the center of a galaxy that's been gobbling up other black holes, gobbling up stars, and it's formed supermassive. We think most galaxies have these supermassive black holes, and the one in our galaxy is called Sagittarius A star. It's kind of a weird name, A star, because it's in the direction of Sagittarius A. If you look up in the sky, that's the direction of the center of our galaxy. And the particular thing in that direction that we think is where the supermassive black hole is, we call Sagittarius A star. Now, if we map out things we see and what their mass is in the sky, we can learn things from these pulsars, these neutron stars, right? We look at all their masses and we see So it's kind of what you're seeing on the left of the plot. You're seeing all the masses of all these pulsars. They're exactly in the mass range we expect, between about 1.4 solar masses and 2.3 solar masses. We see similar things from other, X-ray bursting. Okay, so other cases where we have neutron stars producing X-ray bursts in these binary systems all have mass ranges around 2 solar masses. These are other regions where, now I showed you the examples from LIGO. This is before LIGO. What we did is we looked in also in binary star systems. We could see one star orbiting something else, and using Kepler's law, we figured out, hey, this has a really large mass. And that's what's shown here. Things that tend to have masses between like 10 and 15 solar masses. There's kind of a range here where you don't get much, and that's expected because you can't get neutron stars above this mass. But once you get into this region, you start getting, dead stars from supermassive stars that have left behind black holes. And here we're inferring it from their orbits. We just see the orbit tells us that the mass has to be so large that we think it must be a black hole. Now, just like white dwarfs and just like neutron stars, black holes can be in binary systems. About half of all stars are in binary systems, and if one of the stars was supermassive and died and produced a black hole, then you have a situation that looks like this. You have your star orbiting a black hole, well, they're kind of orbiting each other, but the black hole gets an accretion disk, right? And this is why I said, you don't just see the black hole, you see really an accretion disk. It tends to get super duper hot because you have all of this gas and dust now falling into something that's super compact, generating a tremendous amount of energy. The black hole's rotating, and you tend to get these jets going up along the rotation axis. There's another artist's illustration of Cygnus X1 is a black hole candidate. It's the brightest, most persistent source of X-rays seen from Earth, and it's in a binary system. So we think what's happening is, so first of all, there's a blue supergiant, so star near the end of its life, creating an accretion disk around some very compact object that it's in a binary system with. If we look at the masses from Kepler's laws, we see that the mass of this compact object has to be about 15 solar masses, but the accretion disk tells us that it can't be larger than 26 kilometers. So it's too compact to be anything other than a black hole. So before LIGO, for example, this was like really strong evidence for black holes. Now, I'd say with LIGO, the evidence is almost pretty conclusive. But by the way, these accretion disks produce persistent sources of X-rays. So if we look at a map of our galaxy X-rays, we'll often see little points where there's X-rays coming off. These are often black holes because the accretion disk around the black hole gets so heated up that it produces kind of something that you don't see in normal visible light. It's only if you look at X-rays. Right, so here was our types of black holes. I just gave an example of stellar mass black hole. Let's talk about supermassive black holes, like Sagittarius A star. So if we look towards the center of our galaxy, about 26,000 light years away, from orbital observations, we can tell that the mass of this, the radius of this supermassive black hole has to be less than like the orbit of Uranus or so. That's because we see stars getting that close, right? So whatever's there can't be larger than about our solar system. But if you use Kepler's laws and watch the stars orbiting it, there's, by the way, a picture, right? So we watch all the stars orbiting
Why smell like farting?
this place where we think there's a supermassive black
You
hole.
farted. That's what.
Whatever its mass is,
Okay.
it's about 4
Hey.
million times our sun. Right, and so the conclusion is that there's a supermassive, there's a million solar masses hidden somewhere in this region that we think must be the supermassive black hole at the center of our galaxy. And we call that Sagittarius A star. There's a group that's been trying to image the first black hole. They're gonna they're gonna work on the center of our galaxy, but there's some other galaxies that have even more supermassive black holes.
This one, instead of 1 million solar masses, is 7 billion solar masses. And so they actually were, this was a big news a year or two ago, they were able to image kind of the event horizon region around a black hole for the first time. So they chose to choose one that was relatively nearby and super large. Okay. And so if you zoom in, this is what we can see just normally. But they used an array of radio telescopes around the Earth to try to create an image. It's fuzzy. You can't see much. You should take this with a grain of salt. But this is the first ever attempted image to see what would be basically the event horizon region. And this light around here is complicated because, again, you have light wrapping around in various directions. Here's simulated images of what you might expect to see, which you can compare to what is actually seen. The simulated images show that the light from the black hole, so first of all, there's an accretion disk that's sort of flat, and then the light, depending on, and this is showing different angles that you might see the black hole at. The light gets wrapped around the black hole, right? For the reasons we talked about before, light gets bent around black holes, and it can get bent around multiple times, and it forms these strange patterns. And so this is a simulation of what you'd expect to see at various angles. And so you can imagine, we don't know exactly what angle this black hole and its accretion disk is relative to us. You can imagine, something like this fits the data pretty well. All right, I do think that we're getting low on time, so I think we'll finish this lecture tomorrow, and I'll ask you if you have any questions. Not tomorrow, on Monday. Sorry. All right, no questions. All right, so Monday, not tomorrow. I'll see you all. Thank you, Professor.
Thank you. Thank you.
Thank you.